All right, today we're going to crack open the black box of your smartphone's security. We are diving deep into a massive Google study called DroidCCT. And trust me, it uncovered a fascinating and kind of terrifying illusion that sits at the very heart of hardware security. Let's get right into it.
So, we all have this mental picture of a secure vault inside our phones, right? This little digital Fort Knox where our most important secrets are kept, totally locked away from the bad guys. But what if that vault isn't nearly as solid as we've all been led to believe? That is the exact question these researchers at Google wanted to answer.
You know, it all really starts with what I like to call the black box myth. For years, we've been told that moving critical security functions into specialized hardware, things like a trusted execution environment, or TEE, and Android Strongbox, is the ultimate solution. We just assume it's this perfect, unbreakable box.
Yeah, the promise is a flawless, isolated black box. But the reality? The Android ecosystem is more like the Wild West. You got tons of different manufacturers, all using different chipsets, all running their own proprietary, unaudited code. So there isn't just one black box, there are thousands of different ones, and every single one could have its own unique flaws.
So to actually peer inside all of those different boxes, Google basically had to build a digital telescope. And the scale of this thing is just staggering. They collected and analyzed 1.5 trillion cryptographic samples from over 600 million devices. This wasn't some tiny lab experiment. This was a planet-scale investigation into the health of Android security.
So what did they find first? Well, one of the biggest discoveries has to do with the absolute bedrock of all security: randomness. The best way to think about it is like a fountain. For security to actually work, that fountain needs to be totally chaotic, completely unpredictable. But what happens if that fountain is, well, what if it's broken?
That chaos is what cryptographers call entropy. It's the secret sauce, the magic ingredient that makes your keys and your digital signatures truly secure. And here's the most important part. You really got to get this. In cryptography, almost random is completely useless. It's the same thing as not random at all. Any predictability, even the tiniest pattern, means an attacker could figure out your secret private key, and the whole system just collapses.
So how in the world do you even find these tiny, almost invisible patterns? The researchers used this incredibly powerful tool called the Paranoid Library. And its name is perfect because its entire job is to be paranoid. It hunts for any hint of weakness in random numbers. It's looking for repeating patterns, mathematical biases, you name it. Basically any clue that the fountain of randomness isn't so random after all.
And this chart just says it all. See the orange line? That's what you want to see. A flat, uniform, totally chaotic distribution. But the blue line on the left, that's a real sample from a device out there in the wild. You see those spikes? That is the telltale sign of a broken fountain, a predictable pattern where there should be nothing but pure, beautiful chaos.
Okay, so now that they had a way to spot these patterns, the researchers deployed their telescope for crypto bugs at an incredible scale. This system they built, DroidCCT, is designed to see these invisible flaws across millions and millions of devices at once.
And here's a quick look at how the DroidCCT pipeline works. Over on the far left, you've got these tiny cryptographic artifacts, things like public keys and signatures, being collected from real phones. Then they get processed in the middle and fed into all these different analysis engines on the right, where each one is hunting for a specific kind of weakness. And I want to be super clear here. No private keys are ever collected. They're only looking at the publicly visible evidence of what the hardware is doing.
The whole investigation really boils down to three main steps. First up, cross-validation. Does the signature a device creates actually, work? Does the math add up? Second, the randomness testing we just talked about. And third, and this is the really cool part, a hunt for so-called side-channel leaks, where the hardware might be accidentally giving away its secrets.
And the results of all this led to something pretty amazing, what they call the premium paradox. This finding totally challenges that classic idea that more expensive equals more secure. You'd think the more you pay for a phone, the safer it is, right? But DroidCCT found that's just not always true. In fact, sometimes the highest-end, most premium hardware was actually more likely to fail.
I mean, seriously, the findings here are startling. We're talking about Google's own high-end tensor chip generating weak RSA keys from inside its most secure feature, the Strongbox. Then you had some Unisoc chipsets creating digital signatures with huge chunks of zeros in them, making them ridiculously easy to forge. And across literally hundreds of chipset models, billions of secure key exchanges failed simply because the manufacturers said they supported a feature they never actually bothered to implement.
But maybe the most clever and subtle discovery wasn't about broken math at all. It was about something else entirely. It turns out some cryptographic operations, they have a tell, a sort of digital heartbeat that can give away their deepest secrets.
This is called a timing side-channel leak. The attack doesn't try to break the encryption math head-on. No, instead, it just listens. It pulls out a stopwatch and measures the time it takes to create a signature. If certain operations are consistently just a little bit faster than others, that tiny timing difference, that digital heartbeat, can be used to slowly but surely piece together the secret private key.
And here it is. This is the smoking gun. On the left, you're looking at a vulnerable device. See that clean, clear pattern? The smaller the random number it uses, the faster the operation. You can literally see the heartbeat. Now look at the device on the right. That's a secure one. The timing is just random noise. There's no pattern, no heartbeat, and no leaked secret.
So after finding all these different flaws, what do we actually do about it? I mean, the goal here isn't just to point out a bunch of problems. It's to build a stronger, more secure ecosystem for everybody. So let's look at the big takeaways for developers and security architects. So here it is, the practitioner's toolkit. First, and this is the big one, don't just trust the hardware, verify it. If you're building a high-security app for banking or crypto, you just can't assume the hardware is perfect anymore. Second, isolate the failures. Developers can actually start to delist chipsets that are known to be weak. Third, demand transparency. The paper makes a fantastic argument that open-source firmware is really the only long-term cure here, because you can't secure what you can't even see. And finally, monitor your own data. Those random signature mismatch errors you might be ignoring could be a symptom of these exact hardware bugs.
And all of this really brings us to the final, really provocative question. This whole investigation completely shatters the myth of the perfect, impenetrable black box. It shows us that security isn't some simple product you can just buy. It's a complex, messy, ongoing process. So if even our most secure hardware has flaws, what does that mean for the future of trust in our digital world?